All right, thanks for joining tonight. This is an NZSE webinar. My name's Ken Elwood. I'm a professor here at the University of Auckland and MBEQC Chief Engineer. Tonight we have a very special guest all the way from Chile, Juan Carlos de Llera, who will be speaking to us about resilience, innovation, and implementation. Just before I read out a bit of his background and bio, just want to say for those online, please submit your questions through the Q&A button that should be available to you at the bottom of the screen. For those of you in the room, raise your hand. I've known Juan Carlos for several years now. We're both Berkeley grads, and Juan Carlos was Dean of Engineering at Pontifical Católica University in Chile, which I know as PUC, which always gets confusing because the opposite lettering of the wording. Anyway, PUC, one of the top universities in Chile, and specifically in engineering. Juan Carlos just served about 12 years as dean, just stepping down as dean this year. So I think he's enjoying that the freedom of both getting out of COVID and getting out of deanship at the same time. I've known Juan Carlos also through his leadership of the CIGIDEN Center in Chile, which is in some ways similar to our Quake Core here in New Zealand, and it is in fact that connection with CIGIDEN that has brought Juan Carlos here to New Zealand to give a talk, the distinguished lecture talk at the Quake Core annual meeting next week. And Juan Carlos's experience is vast in the earthquake and structural engineering space. Just want to highlight his contributions in dynamics of structures, particularly torsional responsive buildings and base isolated structures, all forms of seismic protection systems. But Juan Carlos has also expanded well beyond that to have impact on resilience in general across Chile. And so I'm really interested to hear all that you have to share with us tonight and continue on into next week at Quake Core. So I'm just delighted to be able to introduce Juan Carlos de Llera.
Well, thank you very much, and I hope this presentation will be completely different from the one I'm gonna be doing next Tuesday. Okay, so I try to do two different things in order for not boring you people in these presentations. Let me see. Well, it's not working now. Try this. It's not passing the slides. It was working before. Let's see what happened. There you go. Okay, good. Thank you. So the presentation will be mostly on three parts. First, I will speak about the Chilean context. Not all of you know exactly what happens with the earthquake problem in Chile. The second section will be more about the technologies and the applications we have used. Many of them are familiar probably to you, but others could be of interest. And at the end, I hope I can say a few words on what I think it could be the future. So in terms of the earthquake hazard in Chile, we are actually at the convergence of two plates, the Nazca plate that moves about 7 meters per century. That's about the convergence of the two plates and the South American plate. The Nazca plate goes underneath, of course, the South American plate, and we get along this trench different sections where the plate is really locked, completely locked, 100% locked. We've been doing quite a bit of work also in trying to predict future earthquakes in the country. You see in the center figure there that I just put there some of the more recent earthquakes. The 1961 that you probably know is a historical earthquake that was probably 9.6 in a moment magnitude. The one in 2010, you see there, stopped at the top part of the 1960 in Valdivia and others. You still see in the country a lot of seismic gaps. And we're really concerned about some of them actually in the north of Chile, where all the mining in the country is present. The other thing is that in Chile, we've been increasing tremendously the amount of data we're gathering from this earthquake. And when I saw the Quake Core project and making New Zealand as a natural laboratory, we speak about the same in Chile. We want Chile to be also a natural laboratory for earthquakes. So we have an opportunity here of joining these two natural laboratories. Okay, in terms of the data, this is very familiar. We use PSHA for just getting basically our hazard. Chile has, you see in the figure there to the right, you will see here the country, we have different zones. We have a new recurrence model for the ground motions in the country with all this new data. And of course, we use the conventional expression for just computing this mean annual weights of exceedance and getting these hazard curves. That's the typical thing we do. And I guess the data we have today is, I would say, more reliable. We've been developing some of these ground motion models specifically for the subduction zones. One that we don't have is for the vertical component of ground motion. There's one thing that we need to get pretty quickly because we're having some issues also with the vertical motions. We translate that data into our design spectra, and I'm here just presenting to you kind of a reference for the design spectra we use. This is steep soil. This is Santiago, the capital, and zone 2. It's basically we have 3 zones in the country for the earthquakes. I mean, level magnitudes in general. In this case, you see the typical design in Chile is done for seismic isolation, for example, with periods that go above 2.5 seconds. And we use this spectrum here that you see in purple, basically, which is more or less not too different from the new uniform hazard spectrum for 500 years return period. We have another for seismic isolation, another spectrum that we use that is, the 1,000-year return period. One thing that is probably new is that we've been using satellite data for trying to get good information about these earthquakes. And I don't have time here to explain exactly how we do interferometry, but basically we are showing here 2 trajectories of the satellite that really sends the signal, the radar signal, into the crust and gets, of course, the signal bounce back into the satellite. If you look at you take an image, a radar image before the earthquake and after the earthquake, and you just interfere the 2 images, you get a change in what we call the phase. And the phase change has different components, but one of them, the one that is here in blue, is the displacement of that point in the line of sight of the satellite. So if you get rid of several other components, you can compute actually the displacement field of the crust in the direction of the satellite. And we use that for the following. We take that data, that displacement field, and basically do an inversion problem, and we get into the slip distribution of the fault using relatively simple Okada formulas for doing that. So this is the case for the 2010 Chile earthquake, and we obtained from the interferometry we did for the country, the previous figure, the one that was here to the right, that's you see there, I mean, if you look here, the length of the rupture is about 550 kilometers long. Okay, that was 8.8 magnitude earthquake in 2010. You just go back and do this inversion problem, and you get, for example, slips of the fault here of about 12 to 15 meters. The epicenter was here. This is the first earthquake we have recorded in Chile that is called bilateral. It ruptures the fault toward the north and also toward the south. First time in history that we know, of course, of the more recent history. So once we get this data from the slip distribution of the fault, we can compose basically these low frequency ground motions. And we combine that with these stochastic models for the high frequency signals, and we compose the two. And basically we create these synthetic ground motions that, if you integrate them, basically are able to capture the displacement, the residual displacement of the crust. I was really interested in this because we were working in some problems in practice. For example, LNG tanks that had sloshing periods for the fluid that is basically 20 seconds. That's a period for the tank for the sloshing. So I needed data that was useful in terms of displacement and low frequency motions to see if we get the isolation system somehow in resonance, with the sloshing modes and things like that. That was the reason that motivated this part of our work. So basically what we have done today is we have all the Chilean records, taken them and reprocessed them to really capture not only the high frequency part that is always rather well captured, but also the low frequency part. One thing, this is basically the database we created. You can access this today. I mean, we took all the Chilean records and reprocessed them, and they are available in this platform for Chile. This is the database we're using for creating all the new ground motion models for the country. The second context that I wanted to speak about is about the typical Chilean configurations of buildings, which probably are not too different from the ones you use here. But I was really concerned before the earthquake in 2010 with this type of configuration. We didn't have any earthquake for a building that had a shear wall core at the center and a perimeter frame like this. This is very common for office buildings in Santiago today. And these buildings or this configuration was never tested before in Chile with a 1.5 minute earthquake, long earthquake. So that was the reason for studying this. And then we had these shear wall buildings, fishbone type structures that did so well in 1985 in the Chile earthquake that many researchers in the world spoke about the beauties of this type of configuration. Guess what? What worked really well in 1985, which is the building here on the right, didn't work so well in 2010. So we discovered new things here. We'll see right away why. And these buildings on the left, they did incredibly well. Okay, although we were really concerned, they did very well. The question is, was it obvious? I mean, this escaped every single structural engineer in the country. The best ones never realized that this could happen. Okay, and we had this experience in 1985 in the Valparaíso Algarrobo earthquake, and all the buildings in Viña del Mar and Valparaíso, which are the coastal cities of Santiago, did very well. But suddenly we saw this failure, the compression failure of the boundary element, just getting, of course, all the spalling of the cover, then the buckling of the longitudinal bars, and then suddenly the rupture just propagating into the web of the wall. Big thing. 60 buildings like this in Chile. Only one of them collapsed, but 60 that could have collapsed. And actually we started working, and a lot of people, not only us, but many people started working on trying to understand what happened here. And what we discovered right away, this has a lot to do not only with the confinement, of course, of the boundary element, but also with the actual stresses on these walls. Very high actual stresses. If you look at the mean actual load ratio of these buildings, it's pretty low, it's 10%. But if you look at the dynamics of the building, it will get up to 35, 40, even 50%, the actual load ratio. Pretty high, yeah, because of dynamic coupling. And the slabs actually play an incredible role in transmitting, that through shear. So we did a lot of testing with models and things, and basically this is only one example. One building in Santiago. I'm just looking at, for example, here the shear wall Q is, the vertical profile is presented in this figure. And you see here that if I'm plotting the bending moment and the lateral displacement of the roof, the building was doing incredibly well until suddenly went into a single cycle, boom, and died in one cycle. So I ask, my students, I always tell them, where is the R factor 4 or 5 of ductility for this wall? I mean, where is it? What happened to it? And basically, you see here that this happened in a very sharp moment and few cycles. So we started really changing the way we're designing shear wall buildings in Chile. And today we have a much better control of the actual stresses on the walls, and we are checking for confinement and also for ductility of these walls in the design. That was one of, I would say, the most important lesson we learned in this earthquake. But there was another side for the coin, and that had to do with all the seismically protected buildings in Chile. We had 13 buildings in the region where the earthquake occurred. I was, since 2003 and 2010, I was really kind of praying in the desert in Chile about incorporating technology in these buildings. So we tried different configurations, very tall buildings, actually precast buildings, ports. So all these are different, actually, and I think it was kind of a good natural test of these structures that I will speak now more in the next slides. One of the cases that really caught the attention for the professional engineers in Chile was this building, 54 stories in Santiago. It was just finished when the earthquake came. We introduced metallic dampers on these transversal resisting planes here. You see here the configuration. Basically, we just changed the concentric braces and we just cut them and introduced at the center a metallic damper system. These are C-shaped, basically plates. Why C-shaped? You will see because if you see here the red rectangle, we're connecting 3 stories. So basically that damper there is having the interstory drift of 3 stories in that position. So you need a damper that is capable of really deforming that displacement, that deformation. And actually one thing that is important for you to know, those that are not from this field, is that the energy dissipated in any linear system is proportional to the square of the deformation. So if you connect 3 stories, your device is 9 times more effective than in a single story. That's why we cross floors with these devices. After the earthquake, we check, every single plate here. You will see that they are all yielded a lot. Basically, we look at the configuration of them and we realize that probably, we use them up to maybe half of their capacity. That's why we recommended the owner of the building just to leave them there. You could really take them because it's actually these concentric braces are not taking any actual load, so it's pretty easy to replace them. And the second case that was kind of interesting to the community was this port in the south of Chile that was the only one that remained operative after the earthquake. What we did here was an interesting thing. We just interrupted the butter piles in the connection to the deck. And we introduced these tables that you see here in the plan of the port. This is 200 meters long with these 4 butter piles. And we just introduced seismic isolation on top in a way that the lateral stiffness of this seismic isolator is comparable to the lateral stiffness of the vertical piles. So basically what we did is we redistributed all the seismic loads in all the elements of this port, of this wharf. and it worked really, really well. You see here, this is Professor Eduardo Miranda, his gun, okay, by the way. It's a 20 centimeters displacement. Actually, the pipe, this is basically a PVC pipe that just touched the port. So at least we know that the thing deformed 20 centimeters in that port. Okay, so this is basically the motivation for and let's go quickly into the seismic protection ideas. And you know very well the two technologies, energy dissipation. We're just connecting two different points in the structure that have a relative deformation or relative velocity, deformation velocity. And seismic isolation, where you really interrupt basically the connection, the direct connection between the ground and the structure. You can use, of course, the isolation not on a single layer. You can use it at different heights, within the structure. So the only thing that is important for you to know is that in the equations of motions of any structure, what you're doing is you're introducing basically a new term. And that term is basically a new restoring force that will help you just to dissipate this energy that, of course, the ground motion is introducing into the structure. And you are the only, real owner. This is an automatic control problem. You really can control that term. You can control it because you control the position of the devices. You control basically the quantity of the devices. And of course, the type of dissipation you're going to be incorporating. So one thing, it's only one slide that I will tell you about this concept that I published several years ago that hasn't got traction yet, but I think it's important, very important. You can represent every single term of this kind, this term, as a very simple change in supplemental damping and supplemental stiffness. Basically, you are combining here different combinations of damping and stiffness that you add to the structure. Each curve in this plot, let's suppose that we have this 54-story building, and we use a fundamental node. So we reduce dynamically the order of the system to a single degree of freedom system using basically one mode. I'm plotting here the response of that mode, okay? And I have two curves, one for the displacements and one for the accelerations. And the numbers you see in red is basically the reduction, that is actually 1 minus the reduction of displacement and acceleration. This case represents 50% reduction, 40% reduction, 30% reduction, and so forth. So basically, you can stand here and say, if I choose, for example, to add 0.16 damping, a damping ratio into the structure, I'm going to be getting in this system 50% reduction on the deformations and the accelerations. One thing is that you realize that the solution is not unique. You can really use many combinations of stiffness and damping to create exactly the same performance. But the good thing about these curves is that for a single degree of freedom system, you can select where you want to be standing in your design. If you do this is very stiff soil. But if you do this, for example, for Mexico City, these curves will not be like this. They will be almost vertical. Why? Because, of course, when you get resonance, the best thing you can do is add stiffness and get out of resonance. In this case, which is a very stiff soil, if you look at these curves that are more or less horizontal, the best thing you can do is add damping. You just move in the vertical direction and you can really reduce response. So what I'm saying here is with a very simple diagram, you can really define, before you just get into what kind of devices you want to use, exactly the type of design you are going to be getting. You get maybe 80% of the truth with a diagram like this. And of course, you can compute the reduction factors for damping. These are the new ones that we're proposing for the Chilean code. We made a mistake, actually, because we didn't have the data in 2003 when we just presented the first seismic code, that we use records that were compatible to the design spectrum. If you use records compatible to the design spectrum, they have too much energy and they dissipate too much energy afterwards, and they're not realistic. When you use real records, you get curves like this, that the efficiency, of course, decreases with the period of the structure. So we're just modifying our B factors in the Chilean code now by these expressions. Okay, that's enough of the fundamental components, and let's get into the hardware and the applications more. We tried with metallic dampers almost every single thing, geometries, materials, and so forth. And this is only one example of the kind of things that people have tried. The U-shape or the C-shape damper, by far, in my perspective, I think is the most effective one today. But for example, we discovered that if you take copper and you just do annealing with the copper, you subject copper to, I don't know, 600 degrees Celsius here, just keep it for 3 or 4 hours, it becomes incredibly ductile. I did this research work when copper was maybe 70 cents, per pound. Today at $4 or $3.50 per pound, it's basically impossible. But of course, it's also a good material for resisting corrosion and so forth. But if you look at this, you can see that if you apply this into torsion, you get a very ductile component. So you can define, for example, a metallic device, damper, in torsion, and it's incredibly more ductile than if you do it, in tension and compression. Those kind of things are interesting, and we've been playing with them for many years. The disposition of these dampers can be very different. We've used them as lintels. We've been cutting shear walls or whatever in between, also as lintels, in the other direction. And for example, the titanium tower that I showed you before is one example. Also, in the case of buildings like this one on the right here, we just cut the lintel and just introduce, these TARAS devices. The TARAS I will show you in a minute have only one thing you need to be careful, but apart from that, works extremely well. This is actually a retrofit we did in Ecuador for a hospital, pretty old hospital. You see the dampers there. It's, very trivial solution. You just go and wrap, this casing, for the beam, and just get, the dampers underneath here. Actually, I could. Well, there is a video there that maybe you can run it later. But let me see if I can do it. I have to probably escape from the. I don't know how to do it, but anyways. But one thing that is important that I wanted to mention to you is that. If this device gets not only in shear but also in tension, because the hinge here doesn't allow the vertical motion, then your device will not work. What you need exactly is that this goes only in shear, and the plates, when they bend, this point will move up and down, and you need to allow that motion. Otherwise, you're going to get a membrane action on the plate that will basically kill your ductility. That's a very important thing that we discovered after many testing. The other things we have done is basically self-centering systems. I know there are many ideas around this, but the concept behind is very similar. We were trying to find these flux-shaped behaviors with zero residual displacement. So you get hysteretic behavior, but then the system self-centers. And actually, the principle that is behind is very simple. It's basically, in this case, we have these springs here on this side that are pre-stressed, basically pushing, two surfaces that are going to be sliding. This is Coulomb friction, basically, no more than that. And when these wedges get into the narrower part here, of course, the actual load on the springs will increase, and of course the friction force will increase, and you start getting this behavior like this. But since it is an inclined slope, when you change direction on the friction, basically remember that this friction cone is always, the axis is the normal to the surface. Then you get the idea, the help of the angle, and then you get this reduction here, and you move on this direction. But it's always the same principle, that you slide on an inclined surface like that. And this is only one example of making that a physical device that we developed for friction. A bit more sophisticated case is the use of piezoelectrics. Piezoelectrics are incredible materials that they work in two directions. If you applied a mechanical stimulus here, it will create a differential in voltage. But if you apply differential in voltage, you're going to get a mechanical response. They work both directions. So basically, what we did, we introduced, for example, in this case, our plates are sliding one respect to the other, and we introduced these piezoelectric elements here. So they react, and we applied a very small voltage here and increase the actual load in a semi-active way. So we decide what kind of friction we want for every specific moment on the device. This is, of course, this is a prototype for a laboratory. This can be improved tremendously when you just go into production of things like this. The result is this. You get, I mean, you can control friction as much as you want here. Of course, we were not very successful in this dynamic range. We got only a factor of 1.9. I think if we get more creative, we could really increase this range for just modifying friction. The idea is to not to have a single device during the earthquake, but have multiple devices depending on the response you wanna optimize. That was the idea. Another application that was, I think, of interest is the use of viscoelastic dampers in precast structures. These structures had some issues and problems also in 2010. This is a beam column dry connection here that has basically no ductility at all. So what we did is basically to introduce a joint here that actually looks at the geometry of the rotation of the beam relative to the column in the right place for just getting this element that will basically, when the two elements change the angle in between them, basically will dissipate only as a sandwich there of a viscoelastic material. The beauty about this project is that we did it without interrupting the operation of the distribution center. We just went up there and just put all these cases here and just put the devices, perforated the columns, and the system was a system with, I mean, a much bigger damping than it was from day one. Here is the solution seen from the bottom. The other thing that happened to these structures is that most of the bracings at the roof, they collapsed in another distribution center, and we just put here a frictional fuse. Basically, it's a very simple system that controls friction force, and so the bracings, never buckle, essentially. That was pretty simple and another low-cost solution. When we move into viscous dampers, the trick here is basically the one that is shown in this figure, that you have force and velocity. And you want this force and velocity to really saturate. If it doesn't saturate, you're going to kill the joint. So we need this to be like this, and for that, of course, you need to create or obtain a behavior in the silicon fluid that is called shear thinning. Basically, you can really control this behavior only by using the appropriate fluid. That is exactly what we do. This is one test that we did for the Panorama building in Peru, and basically you see that your model expressions basically match almost perfectly well the testing. One thing is that it also matches well the dissipated energy and also the increase in pressure within the damper. Of course, when you start dissipating energy, of course, the pressure within the damper will increase tremendously. You will see here that we can get up to maybe 250, almost 300 bars within the damper. So it's pretty, you need to design that damper for that increase in internal pressure when it gets really hot and dissipating energy. The modeling is simple. The modeling is basically a Maxwell element that you get a nonlinear damper here. Remember that this is basically, I didn't mention this, but velocity is to the exponent alpha. We use alpha usually equal to 0.3 in our designs. And basically we incorporate a elastic element in series with this nonlinear damper. And you just create this behavior that has basically the reason for this cycle here is basically compression of the fluid. You need to capture that part. And the applications are basically in hospitals. This hospital was very interesting because it has seismic isolation, but also the towers we could not control the displacements because they are very, very flexible. So we introduced dampers in this toggle brace form. And those dampers, basically viscous dampers, since the force is really controlled, as I said before, because of this shear thinning behavior, the joints and the columns could remain the same. We didn't change the size of the columns and beams. That was, I would say, kind of the important thing we did for that element. Well, this building, is actually a different application for wind. Of course, the design of the dampers is for wind, but also has to be present for seismic action. The idea here was to control vibrations due to wind to less than 10.2 milli-Gs for a 1 year return period in wind. It was a pretty kind of a specific design. We are introducing 28 viscous dampers with toggle braces in this case, because deformations are too small, or 2 millimeters, and we need to amplify those deformations for, of course, using the dampers. These dampers are relatively low in capacity, about 5 tons, but need to be resistant, basically, deformations, for a future earthquake as well. This is a project that is being led in structural engineering by Maud McDonald. The disposition of the dampers, as you see here, there are 28 dampers in the whole building, and they are located in these 2 resisting planes. This is a building that has a very strong asymmetry in the X direction. And of course, the torsion that is created here is controlled by the orthogonal resisting planes. So also the dampers would help slightly on that part. Because of that, we thought that we proposed actually to use a tune mass damper here on this side of the building to control the torsional mode of the structure. But at the end, it was discarded. I will show it in a minute. But it's a very interesting tune mass damper, by the way. The toggle braces are very simple. You see here, they just cross the beam, and basically there is the viscous damper. The angle here is 6 degrees. The amplification we get here is about 5. So basically, these 2 millimeters just change into 10 millimeters for the viscous damper here. And I went to the construction site yesterday, and you see here their toggle braces are basically already at the site. These are the dampers. As I said before, the force velocity expression has this alpha coefficient here. In our case, this alpha is 0.3. Okay, these are 50 kilonewtons. Dampers are pretty small, but need to be very, very precise. So they're going to be testing, before we install the dampers and after the dampers are installed. Also, we need to simulate. We did a multi-physics model here for simulating the dissipation of heat. That's why you get these nerves here in the casing of the damper to be more effective in dissipating heat. This idea, well, you'll never see it, but I just wanted to mention this. We introduced this idea of the tune mass damper. It's a tune mass damper that was synchronized in the 2 different lateral directions. This was the design. Basically, you see here that there is an element that I'm showing here with the pointer. That element basically changes the length of the cables, so you can tune the frequency in one direction, and you can tune the frequency in the other direction. So it's a single damper that tunes the 2 frequencies, which is a kind of interesting thing. At the bottom, you will see this pantograph here, just to avoid rotation relative to a vertical axis. And we're using these 2 viscous dampers that also had an interesting thing. For wind, they had this performance, and for seismic, it had this larger performance. So we designed a damper that has these different 2 behaviors coupled in a single device. It's really a shame that we are not going to see this implemented in the building. In other cases, the tune mass damper solutions, this is for the Chilean typical residential buildings. We just use masses on top of seismic isolators. All these spaces here, we just fill them with these grinding mill balls that we use from the mining industry, and we get a very heavy concrete there for just having these devices. We usually take 2 dampers on top of the building to control the lateral modes, or sometimes, one lateral mode and one torsional mode, basically. These are a type of buildings we're incorporating tube mass dampers in Santiago. And a final solution for tube mass dampers that was implemented in 2010 is basically a magnetorheological damper we just put on top of this building here. I don't know if you are familiar with the concept, but it's a viscous damper, essentially, that you can change viscosity when the fluid goes through a magnetic field. And you can really control the magnetic field with coils. It's pretty simple in milliseconds. So you can have a damper that is 1 ton or 15 tons in capacity in 1 millisecond. So the idea is to select the right damper at the right moment in the response of the structure. So we implemented this on this building with this pendular mass that we have here. Then after the earthquake, we decided just to go for a much bigger implementation. This is the damper. You see the 4 coils there. Those are the coils where you're going to have creating the magnetic field. So the fluid will just go through there and will become basically a solid when you just go through there's 2 or 3 producers in the world that produce that magnetorheological fluid. One is actually in the US. And so the damper is underneath here, the tube mass damper. And basically the idea, of course, that the tube mass damper, if you do not introduce damping, basically the energy of the tube mass damper will return into the structure. So you need to dissipate it somehow. And this is the whole system we just did for doing that. Probably the most novel thing that we did in this case was with the control of the mass on top of the building with a physical control. If, for example, the mass is going one direction and the building is going in the other direction, we just engage the damper. If the mass of the tube mass is going in one direction and the building in the same direction, we just release the damper. Those kind of things. I'm going to go very quickly on this because this is more familiar with you. Seismic isolation, high damping rubber bearings and lead rubber bearings. One thing we're going to be implementing in OpenSys this new model that has all these behaviors, the stiffness degradation due to a scragging and Mullins effect. The ones you see here is not that simple. The isotropic hardening that you see here, the cavitation of the rubber also. When you get tension on the isolators, you get cavitation. You may have cavitation, so we need to incorporate that. The unilateral effect, you see that the behavior in one direction is almost the same in the other direction, so we need to be able that the model captures that, and the P delta effects. All this in a single model is basically what we're doing, and we're incorporating that in OpenSys. You see here, for example, the behavior for 2 axial loads, different axial loads, the red one and the blue one with higher axial load, you decrease in lateral stiffness. And that is already, for those who are designing buildings with seismic isolation, the way we incorporate today the P delta effect, that is very, very important, the moment that is created by the P delta effect, we have to do it as a different load. We cannot do it, with the same model. Even the models that OpenSys has today is not really included, correctly the P delta effect. In terms of frictional pendulum, we've done a lot of work and analysis. My interest here is basically on the axial loads on the FPS, because there is a comment that is circulating around the world that the FPS can control torsion in a building naturally. Because of course, if you have an eccentric mass, the masses will be, loading more some of the isolators and the system will be controlled automatically. It's not true. What I'm showing here is that if you, for example, incorporate in this very simple case, a mass eccentricity of 0.3, one of the lengths of the building plan, you're going to be increasing the axial loads in the system, sometimes even 6 times because of the overturning of the building. The building will, of course, load more. Some isolators will create higher frictional forces, and of course, with the other component of the ground motion, you're going to get rotation. So this is not that simple, and that's why it's so important just to model this correctly. One of my ideas for a long time was to create isolators of very low cost, especially for what we call social housing in Chile. And one way of doing it is very interesting. Rubber in tension is three times more effective that rubber and shear. So that's pretty easy. Then change rubber and shear to rubber and tension. So we developed this device here with these tendons here that they buckle, as you see here, when they go in one direction and they extend in the other. And it works really well, basically, and you can get, a very good, lateral stiffnesses of the order of 0.5 to 1 ton per centimeter, which is reasonable for this housing. So we implemented this in different places. The other low-cost solution for seismic isolation is to have a slider and a ring, for example, that is full of just rubber with no steel seams or anything. Very simple. This, of course, the ring works as a spring, and the slider is basically the one that is dissipating the energy. Look at the force deformation cycle. It's just perfect. Easy to do, implement, and it's about 20%, 30% the cost of the normal isolator. So those are the kind of things we're really interested in trying to promote and use. I've been in a position in my last 5 or 10 years of just giving away all the information, no patents, no anything. I have no interest in IP. So that's why I'm presenting all these ideas and things. And another one, a final one that I wanted to show you is for special places where the soil is not good. So we use a pile that actually has a rolling surface. It's basically an element that has basically a pre-stressed tendon here in the center, and you can define whatever geometry of the rolling surface you want. You can really control exactly your force deformation cycle depending on the geometry of the rolling surface. And we implemented this in a house in Santiago that was present in 2010. It's like a house on top of rollers, and it worked incredibly well. And here you see the example of the piles, of the house, and we use a single rubber isolator just to make the system self-centered. And I will just finish quickly. The new airport in Lima, for example, we're just working today. I wanted to show this example because one of the big issues here has been the uncertainty on the properties of the isolators. So we had to do basically to run testing of smaller isolators just to get basically the viscous component of rubber that we haven't done before. We could not test this with the capacity we had in Chile, so we had to test it basically a smaller damper and create the factors that we need to incorporate for the upper bound and lower bound stiffness and capacity of the isolators. The uncertainty here is pretty high. You see here, these are basically curves that we have obtained we've tested more than 5,000 isolators actually, and so we have all the databases for those isolators, and we see here for different shear deformation levels, the type of uncertainty we get in the isolators. Controlling today the stiffness and the yield capacity at zero deformation is basically what we are trying to do in these buildings. This is the LNG tank that I mentioned before, just for controlling torsion. And one of my final examples is basically this basilica that is basically destroyed by different earthquakes in 1985 and 2010. This is a beautiful, beautiful building. And the way we're planning to do this is basically first to stabilize the structure. This is already done. And once we have stabilized the structure, we're going to go underneath. Basically, we're going to build these collars on the foundations, just put these piles here, then excavate here, then build, the underground, put the isolators, and then just cut the piles. That's going to be the process we're going to be implementing in the next years for this building. Okay, and timber buildings, a fantastic building in the south of Chile, it's completely timber, but you see here it has 4 cores that are concrete. When you get this type of structure, what happens is that core will just capture all the seismic load. And of course, if you put isolators at the bottom, you're going to get tension on the isolators. So what we're doing is basically take these shafts and increasing the legs so we can reduce the actual loads. basically, a very simple thing, and we're implementing this type of solution with frictional pendulum devices. We're also doing the highest building in Latin America for seismic isolation, 35 stories. This is pretty important, and I mean the tension in the isolators, we have to reduce them by increasing the size of the isolators, but it's nothing more than just increasing and reducing the actual stresses on the isolators. And a lot of healthcare projects in Chile that are already being implemented in seismic isolation. This is the costs in Chile. You're going to have this presentation. So 1 UF, the unit you see here is basically $36 US. You can see how much. This is the summary of all the projects we have done in Chile in terms of cost for seismic isolation, energy dissipation, and Tillmans dampers. And in the case of energy dissipation, we have the frictional component first, and then we have the viscous part. Let me just finish. I was speaking a little bit about resilience, but it's basically what we're doing is basically, sorry, I went the wrong way. Oof. Yeah. Oh, no, I went the wrong way. I can go to the end here. Maybe it's okay. No. Sorry. This is just to give you 1 minute thing. We're incorporating resilience evaluations of buildings in Santiago. Fragility analysis, full fragility analysis of the buildings. Of course, just to make sense of the isolation and energy dissipation incorporated into the buildings. We're following, FEMA P58 procedure quite well, and basically producing ratings for the different buildings in the country. Just to finalize, I wanted to say that at least in my impression, seismic protection today is a very mature field that will explode at some point. I'm pretty sure once the benefits are really better known by users, especially when you look at the life cycle of a project. If you look at the direct cost today, we are having always this kind of conflict between that you're not seeing the whole life of the project. The second thing that is not really well done is that to get the way you're getting seismic protection into codes. And I think there's a lot of things there to do to make this more effective, and that could be also another important thing. But however, the most important one is to try to incorporate in all these analysis the fragility analysis. Really look at what's going to happen to this project, not only in terms of direct costs, but also in terms of the complete life of the project. I think when this is done, seismic protection will be obviously a pretty dominant technology, I think, in building practice. Thank you so much for the patience.
So just what we're going to do, for anyone online, if you haven't entered a question and you've got something you'd like to ask Juan Carlos here, please just use the Q&A function on the webinar link and we can put that question. At the moment, there's only one question online. It's from Alex Shige. It's asking, you showed several examples of designs done with viscous dampers. The performance, energy dissipation of these can decrease considerably under repetitive cyclic loading, e.g. a windstorm or a long duration earthquake. Do you consider such performance reduction effects during design, or would you assume properties based upon some set of initial temperature?
I didn't get the whole thing, but I mean, we're using reduction in capacity of the dampers because of temperature and all those things. I mean, that's part of the design. We're not assuming initial properties, thinking that the damper will be with that coefficients, the whole time. So basically, yes, we try to model things, in that way. And in the case, for example, of wind, the Seascape Tower, for example, that was a big issue. Actually, the number of cycles is huge. So we needed to really model the dampers, for the whole history of cycles. Yeah, and you reduce, I mean, capacity is reduced significantly because of the cycles. Yeah.
So yeah, for Ken.
Mark, great presentation.
Thank you.
Experience. Obviously, you're showing lots of unique devices that are installed and used in different buildings. In Chile, do you have some kind of process to evaluate the devices as they're developed and patented by companies? Some sort of methods that ensure that the innovation that's brought forward is still robust, and even if it hasn't been used over and over again, like our sort of conventional structural systems.
Yeah.
So can I just, I'll just summarize that for
Yeah,
those online.
please go.
So Ken, I would have just asked a question about, there's lots of innovative technologies being presented, and is there sort of a certification and testing regime that provides certainty of performance of those, given they might not undergo quite as extensive testing as traditional structural systems might?
It's a very important question, Ken, and of course there are in the case of isolation, you're forced by the code to do a very specific testing procedure always. So you cannot escape not only the prototype testing, but also the quality control testing. This is very important, very important. Sometimes people tell you, this device I tested somewhere else and it did really well. No. You want to see that every single device really works well, because I mean, if the lining of the FPS or whatever, is damaged, I mean, you could get a big problem, or the rubber compound is not the one you wanted. So that's one thing. For the energy dissipators, we do not have in Chile still a code. So basically what we're doing is we're forcing that in every single project, that the devices need to be tested as well, but it's not explicit in a code. And this is one of the things, because we're working now in a new code in Chile for energy dissipation that will include a section on this respect, on the testing capacity of the devices. You need to do it. I mean, I should emphasize this very strongly, that it has to be tested every single device, not only as a prototype, but also in terms of the quality control of the sliding friction and everything. Yeah, it changes a lot. There is quite a bit of uncertainty. I show you there very quickly then the curves for the compounds in rubber. Rubber, basically natural rubber, and the compounds you have for isolators is basically like a recipe for any food you prepare. You can have exactly the same ingredients. You just put them in the different calendars and different processes, in the manufacturing of the rubber isolators, and you're going to get a different isolator because temperature was not exactly the same, pressure was not exactly the same. The oil you use for just smoothing, the mixture was not the same. There's so many variables in that thing that's why you see those curves. That even though we just aim to let's say, a shear stiffness of 8 kilograms per square centimeter, you get 7, you get 8.5 or 9. So that's why it's so important to control these devices. Yeah.
There's a question here.
Yeah, just I know like New Zealand, they chose to put a refinery up north because it had low seismic or whatever. Does Chile have the equivalent for like some of their big like industrial plants, or is there a low seismic?
Low size.
Yeah.
So I guess just a quick summary for those online. Question was about the location of, I guess, the Marsden Point refinery up at Northport, essentially locating critical infrastructure away from lower seismic areas, and whether or not that's a practice applied in Chile.
I'm not sure that I got the question right. You're speaking about seismic protection in low seismic areas? That's it?
Or you're just talking about locating?
Yeah, just general location of like a hazard facility in a low seismic area rather than a higher seismic area.
That's the question.
Mm.
Are there low seismic areas in Chile?
No.
Yeah.
No, we don't have the case.
You don't have that luxury.
Yeah, we don't have the case. The only part in Chile where there is a lot of debate in in terms of the seismic intensity is in the very bottom in the Patagonia region. There is a lot of people studying that area because we haven't had, you know, a big motion, ground motion for centuries, but it's the only part of the country. In that case, basically the code is incomplete. Our code is completely incomplete. There is even no specification of the earthquake hazard in that region. We don't have data. That's why we're just looking at that. And
so,
mhm.
just in case that wasn't clear online, Keno would basically tip in saying, do you have that luxury of actually having low seismic zones in Chile? And
yeah,
like not.
As I said, we have only this part of Patagonia that is pretty empty region. I mean, there is no cities or anything. Well, Punta Arenas is one of the places, you know, the southern city. And in that case, the design is basically with low seismic design in general, but the information we have is pretty poor in terms of this is a huge debate in geophysicists in Chile about the south, what happens in Patagonia. Yeah.
There's one question online, just a little a hard one to answer, but it says, if you're not interested in IP, what is the best way of implementing these ideas in the real world? So I guess the trade-off there between perhaps having a company where there is a profit incentive to develop a concept and support the implementation versus the potential boundary of having it locked behind a IP protection. So
let me see that. This one.
I guess yeah, patenting something has both a
no, I was for many years. I belonged to the university in Chile. I was the dean, so I have to be careful with what I say. But to be honest, I mean, the university was really enthusiastic in promoting IP for many years. And what happened and I did, and all my patents are basically, they belong to the university, but they're not used. So what's the purpose of having patents that are not used? So in this respect, I think we need to be more flexible in that respect. I mean, some of these ideas we are using, for example, for the low-cost isolation, they could be today be implemented in many social housing in Chile, and they're not, because it was somewhere, you know, a patent that basically no one wanted to really pay, you know, the royalty or anything. So I guess the approach, I think, is not correct for just massifying the technology. I think we need to be much more open in this respect. I have an advantage because, you know, the company we created in Chile belongs to the university. So basically what I do is we take the talent from the students and the talent from, you know, all the research, and we are just a bridge between the university and practice. We never wanted, for example, to design projects in Chile. We only wanted to introduce technology. Today we're doing more projects because if you don't get the efficiency in the design, people will not buy the solution with the seismic protection. For a good solution in seismic protection, you need to incorporate that from day one in the architecture, in everything. You need to optimize the project a lot, and just to whatever, you know, cost you get on the isolation or the protection system, you offset, you know, with reduction in detailing and other things in the structure. We have many projects in Chile that the cost of seismic protection has been zero additional cost, zero, because you just go into the foundations and reduce many things. And I think that's kind of the purpose, even though I know that the decision should not be taken based on direct cost. That's the way things are done so far as well in Chile. So.
Question here from Tony.
Yeah, I think you sort of touched on what my question was, is what proportion of clients in Chile demand or know about seismic protection systems, and when you predict the explosion in that field will occur, and what would be required for it to happen?
So if I can just summarize that for online, Tony Holden is just asking essentially what percentage of clients in Chile might be aware of the existence of seismic protection technologies and might sort of require push for those to be implemented, and when might that explosion in demand occur?
Still is very small. I mean, they're really aware today of the technology. Everyone is aware of the technology. But somehow the process is something they have not incorporated, kind of the normal things they do for a project. It's not a design, because today, for example, our students, they follow the courses in seismic protection within the university. They know how to design these devices. So there's people already preparing the country for doing those designs. The problem has to do more with the effort that the construction company needs to do for example, in the case of seismic isolation, all the gap is one issue. The flexible connections for all the piping and things, all those things, they get a little bit, complicated. We try to convince them, looking at the insurance premiums. Actually, we work with insurance companies for a long time, but the problem with Chile is that the country is still small in terms of insurance industry, and all the reinsurers in the world, Swiss Re or whatever, Munich Re, they look at South America as a single thing, so they cannot distinguish between a hospital that has a seismic isolation from the whole bulk of hospitals in South America. That part still needs a lot of convincing. So the explosion in Chile occurred in 2010. If I tell you what happened after the earthquake in 2010, everyone wanted a building with seismic isolation in the city. We didn't have the capacity for just doing it. But then people start to forget about that, and 4 or 5 years later, we're back in the same equilibrium we were probably before. So that's the situation. We have in Chile about 10,000 buildings that could have seismic protection, and the number of buildings we have today seismically protected is about 150 of the 10,000. So still is a very small proportion of the buildings.
It's
Back here.
The experience is very similar across the
Yeah.
So one final question based upon a question submitted online. I'll just bring it across here so you can see it. In New Zealand, some engineers define some locations for dampers or isolators randomly and then check the behavior of the structure using nonlinear time history analysis. How are you defining the initial location using simple linear methods to get the most cost-effective solution, price against force reduction for a building, and then to check that using nonlinear time history analysis?
I should have. I have a good tip for the person. If you there is actually an optimum for the location of dampers in height or in the structure. Actually, the optimum is not the recommendation I will gonna make because of a reason that I will explain in a minute. But if you want to control a mode, let's say you want to control the fundamental mode of a building, you will realize that the optimal location for damping is the story of that building where the maximum interstory deformation occurs, to the square. There is a square that belongs in that thing. Okay. But of course, it's the same as the maximum interstory drift. So the optimal distributions are always localized, which is very bad in terms of you cannot get all the damping in a single place in the structure because you're going to kill the nodes. You're going to kill, so you need to distribute it, but try to distribute it around that optimum in a location. So we tried distributions, and the best one we've gotten so far is that we distribute dampers according to the square of the interstory deformation. So you take all the interstory deformations, let's say a building, and you compute the square of those interstory deformations, and you just normalize respect to the sum, and distribute according to that proportion. And it works incredibly well. It's not the real optimum, but it's a good one.
Oh, I think we might stop the questions there. There's been a lot of good debate and a fantastic presentation.
No, thank you so much.
This is the hybrid model. We're having an in-person seminar with the live stream. It is a model we're looking at applying intermittently throughout the rest of the webinar series. So this is intended to be the first of a series for the rest of the year. And we will announce those in progressive order. So please keep an eye on your emails from NZSCE, and we'll have additional webinars coming out through the series. So thank you very much, everyone in person and online. And we'll just draw tonight's webinar to a close there. Thank you very much.
Thank you.